Hello everybody, let's take a look at AP Chemistry Unit 1, and we're looking on this particular video at Section 1. And the theme for Unit 1 is atomic structure and periodicity. Now, atomic structure, we'll do a little bit of review again about the nucleus and where the electrons are. And then when we get to periodicity, it's the basic periodic trends that we see. We're going to focus primarily on the electrons within the atom because that's what makes the chemistry happen. Now, the study of the electrons largely was done in terms of radiation, in terms of frequency and wavelength, and Max Planck was one of the people that contributed to this understanding. So it's looking at the energy that's involved through the wavelength of electrons, first of all. Now, this is actually a derivation of Einstein's equation of E equals mc squared, energy equals mass times the speed of light. Now, electrons do have mass, not very much, but they do have mass in here, and so this is a derivation from that. And so Max Planck's equation is measuring energy in joules. The United States equivalent of that would be calories in small c. We do have kilojoules, that would be our big C calories that you see on food labels. And that will equal Planck's constant, and we will measure in frequency of hertz. Okay, now taking a look at this basically a graphic that will walk through the different wavelengths or frequencies that we have here. We'll notice a couple of trends that I want you to pay attention to. You're going to be answering some questions along the way, and they're going to be math-based questions. So we want to make sure we're referring to this properly. Now, first of all, we're seeing as we increase wavelength, we're getting bigger as we go to the right. As we're increasing wavelength, our frequency is actually decreasing, okay? So what that means is the size of those waves are going up and down on a larger scale versus a smaller scale, and the number of times that it's going to be doing that is going to be a lot slower in this distance than it is in this distance, okay? So that's what we mean by frequency of that, and we have graphics of the different wavelengths that we'd see out there. Everybody's familiar with X-rays. We have UV light. Then we have the visible spectrum that runs from about 380 to 750 meters if we're looking at our wavelengths. And then we get down into infrared, microwave, FM, AM, and then our long radio waves. So those are all the different types of waves that we see there, and we'll be referring back to that from time to time as we answer some questions and take a look at electrons along the way. Okay, so let's take a look at some more information with these, and we then see, as I said, that the Max Planck's equation was dealing with Einstein's equation of E equals mc squared, so we can derive that even further and see that the speed of light is a function of the wavelength as well as the frequency, because we do have those correlations. And then we can then combine all these facts. If we are given a wavelength, we can find frequency. If we have given a frequency, we can find wavelength. We can do all those things or equate them all into energy, and that's where Max Planck's constant will come in. Okay, now from all of this, you might be wondering, okay, big deal. What does this have to do with chemistry? With all of this, then, we can actually take a look at some physical properties as we add energy to an atom. Then what's going to happen is the electrons are going to jump out an energy level, they'll collapse back down, and they'll emit that energy that they temporarily stored into a wavelength of light. And we can see those wavelengths as we see on the graphic that's up here on the spectrometer, that we have a wavelength that's given off, and here we have a single bar, and this is of helium. And so I can see from this, it's just slightly more than 650. It's about 660 nanometers in this particular case that's being emitted. And from this, I can see the energy and I can correlate it with what the wavelengths and frequencies are. And then I can figure out, oh, okay, I can identify the element. Now, this is what astronomers will use to figure out the identity of gases that are found in distant stars that we'll never get to. It's what we can do to figure out the identity of unknown substances that we collect as well. We can actually vaporize it, add energy to it, see what they're going to be emitting with the spectrometer, and identify the structure or the compounds from there. All right, so that's the nature of our emission spectrum lab that we're doing in class. Now, as you take a look at some applications of this, and that's what I want to focus on, is how to pick apart questions like this. All right, we're given a question where we see the blue color in fireworks, so that gives me an idea it's in the visible spectrum, and we see a temperature in here. We're heating up a compound of copper 1 chloride. Now, here's some key things that we see out of here. We are given a wavelength. Now, remember, wavelength is a particular label on here. It's 450 nanometers, and here's the value that we're going to be working with, 4.50 times 10 to the second. Okay, now remember that our equation is E equals h, Planck's constant, times the V. Now that another equation that we could be doing is E equals Planck's constant times the speed of light divided by our wavelength. And so this particular prompt tells me I'm working with my wavelength equation. Okay, so let's pop some numbers in here with that. I'm solving for the energy because it's asking for what's the increment of energy. The energy is going to equal Planck's constant, which is 6.63 times 10 to the negative 34th. Now, the label on there is joules per second. And we're going to multiply that by the speed of light, which is 3.0 times 10 to the 8th. And that's going to be in meters per second. And notice that I'm going to take and write meters per second as an inverse like this. Okay, that means meters divided by seconds, so my seconds are going to cancel out. Now, I take a look, and the wavelength that's being provided is 4.50 times 10 to the negative 7th meters. Now, the question is, how did I get that? Well, this is in nanometers. And so we go back to, here's my base unit of meters, deci, centi, milli, there's a couple spaces, then micro, couple spaces, then nano. And so if I'm going from nano all the way over to meters, well, then I'm going to be moving my decimal. Here's my decimal right here. I'm going to be moving my decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And so that's where this coefficient, it goes from a positive 2 to 10 to the negative 7th. Okay, that's just doing a review of the metric system conversions. And we get a final answer of the energy equals 4.41 times 10 to the negative 19th. Now, this is in meters, and so this meters cancels out. And so my last label then would be in joules. Now, this answer is perfectly acceptable. We could convert this into kilojoules, and the reason we would do that is if we're going to be using a different equation with it. So another acceptable answer would be 4.41 times 10 to the negative 21 kilojoules. Now again, on this side, here's deca, here's hecto, and here's kili. So if I'm in joules here, I'm moving my decimal 1, 2, 3 times. So you see where that negative 21 comes in. So either answer works here, and I see 3 significant figures because there's 3 significant figures here. All right, so there's our answer for that particular problem. And let's take a look at some other applications now. Okay, second equation, or second question, I should say. Now it takes 208.4 kilojoules of energy. Okay, so there's my energy value. All right, so that's important. We're seeing, oh, that's my E value right there. All right, and it takes that much energy to remove 1 mole of electrons from an atom. And the question is, how much energy then would it take to remove a single electron from the surface of the rubidium? So if I'm going to remove an entire mole's worth, it takes 208.4 kilojoules. But how much energy is it going to take for just a single electron to be ripped away? Okay, so we have a couple of issues going on here. I want to remove, if this is my nucleus, I want to remove just 1 single electron off. And the question is, how much energy would that take? Well, I know that it takes 208.4 kilojoules to remove 1 mole's worth of particles. In this case, electrons. And I know that 1 mole of something is 6.02 times 10 to the 23rd particles. That's Avogadro's number. Okay, so I've gotten rid of this. I've gotten rid of a mole's worth. And so what I end up with is 3.46 times 10 to the negative 22nd kilojoules required for every particle. Again, we're referring to electrons. All right, so that's the first part. And it's just saying how much energy. It's just taking 1 single electron out of there when we're given a mole in the beginning. Now, the true question of this is asking, what's the maximum wavelength of light capable of doing this? What wavelength would it take to actually get that when we use that much energy? All right, so let's go back to our energy equation. Okay, so we have Planck's constant times the speed of light, and we have our wavelength, because that's what they're asking for. What wavelength would we get? All right, so let's insert the numbers. 3.46 times 10 to the negative 22nd kilojoules. And that's going to equal Planck's constant, 6.63 times 10 to the negative 34th. And 3.0 times 10 to the 8th, because that's the speed of light. And we're solving for my wavelength. Now remember, we got to get that out of the denominator, multiply both sides by the wavelength, and then I divide by the energy. So my wavelength is going to equal 6.63 times 10 to the negative 34 times 3.0 times 10 to the 8th, and then we're going to divide that by the energy. We end up with an answer of 5.73 times 10 to the negative 7th meters. Okay? 10 to the negative 7th. So if I go back and I consult with that chart that we saw previously, let me back up here. There we go. Oh, we see to the negative 7th. So that means I'm down in the visible spectrum and I'm right around this area of the green wavelength. Okay, so you'll have that reference in there. You don't have to have the numbers memorized, but you do have a reference for that particular type of question. Now, continuing on with the work, we can also find that the electrons, we can figure out the electron wavelengths, and that was Broglie that was working with that. So we're just going to be getting into wavelengths, we're going to be getting into and frequencies and so on. It just keeps on working with different types of questions. And this has a function of their speed as well. Smaller objects will have a larger wavelength, and the larger objects will have smaller wavelengths. It's harder to basically move those things with larger mass. So we kind of take a look at comparing some objects, and we can compare the wavelength for an electron, which has very little mass, to something that's a lot larger, exponentially larger in terms of some kind of ball. Now, there's a key to this, and this is a very typical type of question that we'll find with the College Board. There's actually a couple of points in here. It's a simple question, but you do need to include two different things in this answer to get the full points. So we want to break this down. Now, they're saying to compare. When we have to compare things, we have to do side-by-side comparison. So let's take a look at the electron first. Okay? Now, remember that in all cases, we're going to be taking a look and basically using the equation where we have the wavelength, and that's going to equal h times our mass times our velocity. Okay, and we have the speed of light, but that's going to be constant. So we're, or the speed that they're going, I should say. So that's going to be a piece of that. All right, so let's document what we're given with this particular question. We know that the mass of this is going to equal 9.11 times 10 to the negative 31, and that's in kilograms. All right, and the speed that it's going is close to the speed of light, but not quite that speed. So it's going that 1 times 10 to the negative times 10 to the 7th meters per second. Okay, so let's use the equation and let's figure out the electron wavelength. All right, so 6.63 times 10 to the negative 34, and we're going to divide that by our 9.11 times 10 to the negative 31 kilograms. And our speed, which is 1.0 times 10 to the 7th. Okay, so the electron wavelength is going to be 7.28 times 10 to the negative 11th meters. Okay, now the second part to this is asking about the ball. If we're going to be doing a comparison, the ball. Okay, you can see that the mass is here and the speed is right here, and it is in meters per second, so we're in consistent units here. So using that ball frequency, or wavelength I should say, that ball wavelength is going to be 6.63 times 10 to the negative 34th. Its mass is 0.10 kilograms. Notice that those units are the same. and its speed is 35 meters per second. Those units are the same. So my wavelength for the ball ends up being 1.9 times 10 to the negative 34. Notice that I have two significant figures in this answer because I have two significant figures here. I should have this one as 7.3 times 10 to the negative 11th, four significant figures there. All right. Now, this is one point of there, but they do say to compare them to each other, so just simply writing their wavelengths is not quite answering the question fully. A second point in a free response question, or FRQ, would be to state the actual comparison. So the ball has a much smaller, you don't have to say by how much, but you do have to state that comparison wavelength than the electron. So there's point number two, and sometimes people just see the numbers, and that doesn't quite answer the question. They don't say what are the wavelengths, they say to compare them. Okay, so it's just those little tricks along the way to make sure we're getting the full value for the different questions. Okay, they'll make it harder than it is, but we do want to make sure we're answering it. Now, Niels Bohr then made the next, we basically draw on Niels Bohr's concepts to draw on the next concept. Now, Niels Bohr came up with the Bohr model of the atom, which means that in the center we have our protons and neutrons, and on the outside at different distances or different energy levels are going to be our electrons. Now, what we've been doing this entire time is we've been adding energy to the electrons. And what that does is it excites the electrons, gets them moving faster, and they actually jump out an energy level. Sometimes they come off completely. And if we remove that energy, like I said before, we can collapse that back down, and the electron will, or the atom will give the stored energy off as a wavelength of light. I showed you the emission spectrum of helium. And so we can use that concept to basically see how much energy is going to be emitted, what types of wavelengths are going to be emitted, even what colors are we going to see. Just like with fireworks, what colors would we see as those electrons are jumped back down? And so here's the equation to do that. Okay, the energy of that electron is a function of the Rydberg's constant and the distance that it's going to be, or the number of energy levels that it's going to be jumping. Now, notice that this is a negative value here. Okay, the negative value right here is because it's giving off that energy. All right, so it's just energy being emitted with that. So let's put it in play and calculate the energy evolved as an excited atom has an electron fall from energy level 2 to energy level 1. Okay, we'll talk about electron configurations in the next video, but basically it's saying from this shell going back down to this shell. Okay, now calculate the wavelength of energy. Okay, there's a key word here, and the type of radiation needed. So we're going to go back to our graphic of that wavelength and what that equates to. Is it an X-ray? Is it infrared? If it's visible light, which wavelength of light would it be, and so on. All right, so let's take a look at the equation. Energy equals the negative of the Rydberg's equation as a function of the energy levels squared. Now, energy is going to equal the negative 2.178 times 10 to the negative 18, and that's in joules. And we're going to then divide that by n squared. Now, dividing by something means multiplying by its reciprocal. Okay, so let's multiply by the reciprocal of that, which is 1 over 1 squared, because we're going back down to our energy level 1, and we're going to be going from the energy level 2. Okay, so it's the difference between the energy levels squared. Now again, we're dividing by the square of the 1 minus 2, but let's just multiply by the reciprocal. 1 times 1 is 1, 2 times 2 is 4, so it's 1 minus 1/4. Okay, so it's just using some logic with this. And so we end up with an answer of energy equals a negative, meaning energy is given off, 1.63 times 10 to the negative 18th joules. Always put a box around your answer. The readers will need to know your final answer, where that is, especially when you have limited space for your time, okay? Now, that answers the first type of question. That's the wavelength of energy, okay? Finding where that energy is, getting into those things that I should say that goes into the energy given off. Let's get into then, because that's the first part. The wavelength that's being given off then has to be a function of that energy. So the energy then equals Planck's constant times the speed of light, and that will then give us our wavelength. All right, so 1.63. Technically, there's a negative in there, but the energy given off is 1.63 times 10 to the negative 18th joules, and that's going to equal, let's see, 6.63 times 10 negative 34th, Planck's constant, and 3.0 times 10 to the 8th, that's the speed of light, and we're solving for wavelength. My wavelength then ends up being, what do I end up with? 1.22 times 10 to the negative 7th, and that's going to be in meters. Okay? Now, if we go back, the type of radiation, again, we go back, there's that -7 again. That's our green light. You could say visible light. You could be specific about the green light from the visible spectrum. Okay, so that should give us all the information we need to do problems like this. As we get into practicing it up, we do have problems 1 through 6. We're going to be doing some other things with that, and our next video is going to be taking a look at where do each of the electrons live. Okay, good luck to you guys, and we'll catch on next time.